Good evening, everybody. Got an interesting problem here. We're supposed to prove that this particular number, this irrational number, is a solution to the fractional piece of a number plus the reciprocal. The fractional piece of the reciprocal is equal to 1. We want to show that it's a solution to that. Now, you'll notice fairly quickly that this is a special case of a more general form that's used to prove there's a countably infinite number of solutions to this equation. And there's other forms, I think, but this is just one of them, okay? Now, so we have this. And you can see that this is in this form for m equals 10. M equals 10, all right? And so this is going to be a special case I'm going to show you, but anything of this form, and I think you need m to be greater than or equal to 2 probably. An integer greater than or equal to 2. But in any event, let's go through this special case, 10 plus the square root of 99. And notice how close they are. The square root of 99 is, the square root of 100 is 10, so the square root of 99 is just a little bit less than 10. 99 looks a lot bigger than 10, but the square root of 99 is slightly less than 10. Okay, now this is a general definition of what we mean by the fractional piece. Let's do a concrete example. What if we had, like, say, 4.8? Okay, the fractional piece is always going to be the part of the number that's less than 1. And so this by inspection is just 0.8, or 4/5 if you want to think of it that way. That makes more, you know, we can write 8 over, just 0.8 or 8 over 10 or 4/5, okay? But notice that that's the very same thing as the number minus its floor, okay? So that would be 4.8 minus its floor, okay? And the floor of this integer is, of course, 4. Now, just to do an arbitrary value, you can do it immediately just by inspection, but we need a formal definition of what we mean by the fractional part of a number in order to prove this, okay, in the more general case, and also for the special case, I guess. So we're looking at this. This is the form of our left-hand side, and we're substituting our proposed solution in both spots here. And most of the work I've done for you, let's see, yeah, right here, this part right here comes from the fact that 9 is less than the square root of 99 is less than 10. And then you just add 10 to both sides of that, right? So this is unassailably true right here. 9 is less than the square root of 99, which is less than 10. And so if you you can see why this works out. If you add 10 to this and 10 to this, you get 19 is less than, the square root of 99 is less than 20, okay? And so that proves that the floor of this number would be minus 19, okay? The floor of this number has to be minus 19, and it follows from the statement right here, okay? Again, we're using this part right here, the floor part right here, and this would be the floor of this number based on this inequality, okay? Now, right here, we just did the standard, we multiplied top and bottom by 10 minus root 99. Okay, and remember, then you have a squared minus b squared. That would give you 100 minus 99, which gives you the 1 right here, okay? And so, let's see, yeah, and the rest of it's fairly straightforward. And when you add all this up here, you see that the 99s square root of 99s cancel, and you just get 1. Okay? So we've shown that this is a solution. Okay, we've shown that this object is a solution. Similar objects, like you might consider 13 plus the square root of 168. And when you first look at this number, you go, whoa, it's a big number. But the square root of 168 is just a little less than 13, since 13 squared is 169, okay? So anyway, there you go. We have shown that this is a solution. And I'll do a video later on showing that this proves, this parameterized version of things with m being an integer parameter, proves that you have at least a countably infinite number of solutions to this equation. And I don't think it has any rational number, non-integer rational number solutions. I think that's a nice proof all by itself. I think let x be a real live rational number with no ones in the denominator, like say 7/3. Okay, I think you can show that any rational number is never, any so-called proper rational number is never going to be a solution to this. All the solutions to this are irrational numbers. And this, what I've shown you, is a family of irrational solutions right up here, which I'll prove in another video. But anyway, down here's the arithmetic for the more special case here. Hope all this made sense. I left out some of the details, tried to insert the important facts. All right, thanks for viewing.